everyone. Welcome to this new episode of the Swift Academy podcast. And we try to continue now with the third episode of the iOS mobile security with our special guest, our specialist Dave Poirier, who come from Canada. He worked now at iVerify, and today we will try to speak about. It will be a practical session, very practical session with two topics, such as what we call runtime attacks and how to try to protect from what we call the reflections, etc., that hackers can use on our iOS application. And for the second part, we'll speak about how to secure our API keys. Hello, Dave, and how are you?
Hi, Walid. Doing all right. Looking forward to the session today.
Okay, thank you. Uh, I think that for the two first episode, we have some basics about iOS mobile security, and today we can uh, deep dive into some also practical part, especially what we call runtime attacks. And my first question to you, it's what are some common signs in app memory that attackers may try to leverage from your point of view?
I think it may be worth actually expanding a bit more about what we mean by runtime attack for a normal iOS developer.
Okay.
There's a whole class. Essentially, when we think of attack on our mobile applications, we usually think of like there's man in the middle, or the HTTP may be compromised, or the actual files that are on disk may be compromised. These are all communication attacks or storage attacks. Essentially, the attacker just has access to some of the artifacts that you generate out of your app, like network communication. They intercept the network communication, they observe it. A typical defense against that is TLS pinning.
Okay.
And then there's also like the file artifacts. So let's say you have an app that is running, and you create like a grocery list. You save the grocery list on the file system of the device. Then via like a USB connection or backup or something like that, they get access to your files. So these are like, they don't require any special tools. They're easily doable via like commercial off-the-shelf applications. And then there's the runtime attack, is where the attacker actually gets access to whoever they want to target, their phone, as it currently runs live. This is normally done via spyware or malware, like Pegasus, for example, was doing that.
Okay.
Access to you via zero click on your phone. Then as Pegasus is running in the system, it's able to do all kinds of things, including relaunching your apps with a debugger attached. It's able, so essentially, like if you're running the app from Xcode, they have access to every debugging tool that you normally have, breakpoints, dump memory location, inspect the variables, inspect everything that is going on. So the runtime attack is a completely different class of what we as developer are usually protecting against, but it's more and more common for state actors and for attackers to try to get access to that kind of information, because once you get inside of the runtime, you can pretty much get access to everything. It's just a matter of like how dedicated you are. So this is one of the thing that often comes back through discussions, is like when I speak about security, the first thing that people say is, well, Dave, if they have access to runtime, it's game over. Yes, but it also depends on how much effort they're willing to put into it and how much information they're going to be able to extract very easily. So if all of your strings, for example, on your app as is, like, and then you load your app into memory and all your strings are just strings, clearly, as soon as they have access to the memory, they're going to have all your strings. So if you have an API key that is stored as a string, or if you have anything that is stored, then they have your API keys. So it doesn't matter if you stored it into the info plist of your app, or if you stored it into the project runtime. They eventually gonna get access to your API key because they have access to the full runtime. Your runtime is basically what your app is running in. So if your app is able to get access to that string, eventually the hacker will be able to get access to your string. But it's not because we are able to eventually get there that we have to make the way to get to that information super easy. There's ways for us to make it harder for the attacker to be able to get the information, or at the very least, to not be able to grab it straight from the info plist of your project bundle. So this is what we're gonna touch today: is how can we kind of protect against those runtime attacks, and at the same time, it will also try, because we're doing this for runtime attacks. It also means that the keys are also going to be protected against more simple attacks like grabbing the API key from the info plist. So we're gonna cover those two things.
Yes, and I think that sometimes we have some APIs that exist now in Swift that help us and also helps attacks to make some what we call now runtime attacks like reflections and mirroring.
Indeed.
Yes, yes,
When Swift was first introduced, I was super happy because one of the issue that we had with Objective C is that all of the function names or methods
yes,
are just strings. So you basically say, when you have an object that has, I don't know, a method called print, you would usually the way it would work is that when you put the square brackets in Objective C and you have your object name and print as the method, you're essentially calling an object with object perform method, and then you pass a string called print. And
yes.
so your method names are all just strings inside of your app,
Mhm.
and anything that is observing the memory runtime can see the function names travel by. So it's super easy to observe all of the function name that are in your Objective-C applications. It's
Yes,
super easy as well from one central place to inject, modify the data, modify the call stack, and observe everything, because it's like there's everything goes through that perform method, the function. So, or get implementation. So you have a C function called get implementation. It gives you the pointer to where the object is supposed to be used, and then you have another one that is get perform method. So both of them. Oops, sorry. So both of them are super easy to swizzle or inject or block or put a breakpoint on, because they all go through the same Objective-C base method for executing everything. When Swift was
okay,
released, all of this was gone. We were no longer calling methods with string parameters for the function names. Everything was being compiled. We were able to say, okay, let's remove the debugging symbols, and all the function names are gone. All we have are memory addresses, making Swift a lot more safer. And then they introduce mirror.
yes,
I was like, what are you guys doing? So mirror is a runtime that you can say mirror this object, and it gives you a detailed breakdown of everything that is in that object, all the attributes, the name of the attributes, the values of the attributes, the class names. Everything is super detailed, and you can basically observe. So when you do, for example, print in a variable name, the way the variable is constructed in order to be able to print it is through the mirror, through the reflection.
yes.
So this whole mechanism is kind of built into Swift. You can control the level of reflection, but that reflection mechanism, when I just wanted to slap myself. Like, why the hell would you do that? They even went further than that, and they also made it possible to swizzle or Swift function names, a way
Yes,
to replace them with other Swift. I'm like, this is completely counter to what you want to do for security. In security, you don't want swizzling. You don't want to be able to inspect your object. You want them to keep them like unknown. You don't, and only if you want to be able to print them. But the ability for the runtime Swift to do swizzling, to me, is mind blowing. Why they would even do that? I wish they would allow us to say don't allow swizzling instead of a binary, but unfortunately. They still allow it today. So that part we can't really protect against. But the very thing that we can protect against at the very least is hiding our class names, hiding the attributes, the names, and the values.
but from your point of view, why Apple and the Swift community was creating a reflection? Because I think that some developers think about generic and how we can use mirror to inspect
Well,
attribute at runtime, etc. In our
well,
project, we use mirroring, and
Well,
we have this.
we use mirroring all the time when we're writing the app and
Yes,
when we put a breakpoint and we want to inspect a value of a variable. It's super helpful for us as developers to be able to know what the values of the attributes and what they are. Like, what's the object name, what's the attributes, what's the properties, and we do print our PO, or like even in our logs, we sometimes like have a log statement where that will grab the specific value and print it on screen or print it into a variable. We send it to our logs, server logs, for analysis. So mirroring is super helpful for us for debugging.
Yes.
Or even for tracking live runtime issues. So you have an error, it's nice to have a description of the error. The alternative to erroring would be like the custom string convertible. So you can adopt the custom string convertible, and then whenever you ask for to print the object, the custom string convertible value description is going to be generating a string that you can then send to the log. So you can send your own custom string out for representing your object. But if you don't have mirroring, you would force all the developers to create custom string convertible for every one of their class structs, which would be, I guess, more time consuming. So this is why they did the mirrorings, to just make it easier for us to debug.
Yes, yes, great. And I think that you have prepared some example about
Yes, I have.
using reflection and how we can go with the security finally to have what we call the custom reflection. uh,
Yep.
Yes.
So in the Xcode build settings for your project or your target, there's something called Swift Reflection Metadata level. And this is basically when you compile your app, Swift is going to include either all of the information for each and every one of the classes or partial information. So what you can do is you can say, I want everything but not the name. So essentially the class name will be shown, the values will be shown, but the names of the attributes or the properties of your objects will not be displayed. And then you have none, where basically I'm just giving you the class name and absolutely nothing about anything for reflection. We're going to see how this is going to impact when we run the app. So the first thing that I have is I have a small security app here that has two objects. It has a document object and it has a token object.
Okay.
The token is just something that I have either an external library or just an object that I want to hide the details. I don't want to show the details at runtime because it may contain a username, it may contain properties, it may contain an access token. But whatever the reason is, I want to hide that information at runtime, and I want to protect it as best as we can. So our example will basically run, and then we're going to run the same app with the different Swift reflection levels and see what the behavior is. So when we first run with the default settings that come with your Xcode project, when you print when we do the two print statement that we have here for the document and the can authenticate, what we see here is that the print statement for the token prints all of the attributes of the token. We expect that.
Yes.
For the document has a title, and we can see document title and with the name of the document here. And then the API confirms that the token that we have can be used for making API calls. Awesome. And the token is not a string because it's a secret. And so if we go back in here and we look at the first version of the authenticator, which is the one currently in use, we have a secret. The secret contains the user ID and the permission. And when we call the authenticate function, we just return a secret. And then later on, we call the perform authenticated. We give a secret back. And if it is indeed a secret, then we are good to go. We can proceed with the API calls. We can do whatever we want to that is supposed to be protected. If it is not a secret, then it will return false. So this is what the output is presenting here.
Okay.
So when we create a token, we just ask the authenticator to give us a token. And then later on, we just print it. And then we also have the reflection that's going to show the content of the token itself at runtime. So we run here at runtime and we run the project. We can clearly see that we got the token is a secret. Then it has two different attributes, a user ID that has this value here, and a permission, which is an array of values that we have for read and write. Yes. So this allows the runtime or the attacker of our runtime to have a full detailed breakdown of all of our object attributes, properties, and values at runtime, which is great for them, not so much for us. Yes. And at the same time, for us, it's useful because when we are doing the print statements of everything, during debugging, we want to be able to see what the content of the logs and the documents are. So everything is working as expected. So let's try to start by protecting our token by changing the reflection level. So first we'll go without names, and we're going to see what the impact is for that. So let's rerun the target. So the first thing that we have to notice is that in the logs, in our print statements, the information is gone. All we have is secrets and documents. No detail at all. So you're like, oh, I'm safe. But then at the runtime, you can still get the values because the reflection metadata said without the names, but it didn't say without values. It just says without the name. So now we have we know we have an object that is called secret. It has two different attributes. We don't know what the names of those attributes are, but we can kind of guess based on the values. So we have read and that sounds like permissions, and we have like a value. It looks like some kind of token or identifier of some kind. So
Yes.
we don't know what those values are. It's maybe a little bit confusing, but we can still get the values themselves, which is not really what we want.
Yes.
But it also means that our print statements are way less detailed. So when we're trying to differentiate between two objects or two documents, we can no longer know. Is it the same document? Is it a different document? Is it document 35? Is it document ID? We have no idea because our print statements are no longer helpful.
Yes.
So we kind of didn't really protect the runtime, and we kind of shoot ourselves in the foot by preventing proper debugging when we run the app. So this is really the worst setting that someone could potentially pick. I'm not even sure why they did that. I wish I could have a conversation with a Swift developer that wrote this and said, hey, let's do it without names. Not entirely sure what their idea was, but I'd like to have a very solid discussion with them. Anyway, let's set it to none and see what happens. So now, in the print statement, in a console, we still see only secret and documents, same thing as before. But now, at runtime, we can no longer know how many attributes, what are their values, or anything. We can just say, it's a type secret. So at the very least, we kind of protected the runtime now, at least when they are trying to reflect our object where it no longer shows. But at the same time, we kind of still are unable to debug our code. So we're going to try to improve that.
Yes.
So we're going to go in our authenticator. I'm going to disable Authenticator V1. I'm going to go to Authenticator V2.
Okay.
And essentially, it is the same code. We have a in V1 we had a function called authenticate that gave us a secret. In V2 we do exactly the same thing. We also had a function that was trying to perform authentication. It was just verifying that if what we received was a secret. And in V2 we have the exact same thing. So those two parts are exactly the same. So what we did change was inside of the secret. So inside of V1, we just had a secret struct that had a user ID and permission. But in V2, we now adopt the CustomReflectable protocol.
Okay.
So by adopting this, we now have the ability to return a custom mirror. Essentially, we decide what we're going to return for when they try to reflect the object. We say, instead of reflecting the object, I want you to reflect this. And you can pick and choose which of the children you want to release. You can pick and choose the class name here. You could do secret.self here or just secret,
and return.
And it would work, and then the reflection would work the same way. Or you can just say self. So I want you to reflect self, but out of my children, I want you to just say user ID is blank. So now if we run this, I'm gonna go back to re-enabling all the reflection just so that we have all the details. So now when we run this, we have one attribute, user ID, that is nil, but that's not really the value, but we could, if we want to, return a different name to confuse the people. So we could say, I don't have a user ID property, but what I do have is cookie type.
Something,
and we can say oatmeal. And now suddenly when they're gonna observe the thing, they're gonna say, well, the secret has a cookie type oatmeal. What the hell? It's a secret. It's no longer an authentication token, but so you can kind of use the custom reflectable to return whatever you want, either to confuse the attacker or just hide it. But it's up to you to decide what you're going to reflect. So the custom reflectable is really useful for trying to confuse. At the same time, in our logs, it becomes a little bit more confusing. For example, we know that we have a token that is something that is released. It's a secret that was created by the authenticator, but we don't have any details. So the string is not really useful, which is great because we didn't want the string to be useful for the token. We're trying to hide it. And at the same time, the document title, which is non-protected, we are able to debug it. So this is the best of both worlds. So we still allow Swift reflection metadata, but we control what the reflection will be.
Yes.
Unfortunately, this really doesn't hide the type. So when we are printing the token, the secret that we're trying to do, either in the print statement or when we run the app, we can still know that it's a secret. Yes, we can return different children. We can confuse the people a little bit by returning attributes that don't really exist or don't make sense or confuse the people. But we'd like to be able to return a different value for the reflection altogether,
yes.
so they don't even know it's a secret.
Yes.
So let's go in V3 and do that. Oops. So in V3 we have exactly the same thing, an authenticator that just returned a secret and just validated the secret is the same. And then the only thing that we did differently here is first we returned a different class for the mirror. So in V2 we were reflecting self with different attributes. And in V3, we're going to reflect a string, or it can be anything. So you could create another type here. I don't know. Let's call it struct recipe, or cooking recipe. Cooking recipe. And let's do this. And then in here, when we reflect, we can say return the cooking recipe, no children generated, and then
something, yes.
And then
Yes.
when we're gonna run the app, what we're gonna find is first, your token is a cooking recipe for oatmeal cookies.
The type is cooking
And
recipe.
then the type says cooking recipe.
Yes.
There we go. So now when they are doing a reflection, they don't think that they even have a secret anymore. They think they have a cooking recipe. So you can completely confuse the attacker when they try to observe what the objects are supposed to be by misdirecting them to a different type that is completely normal. So you could even return back the document. So we know that we have a document type. So here I'm just going to return a document. It is right here. It's a type that exists. It takes a title as a parameter. So we can say title Little Red Riding Hood. And it will have one attribute called title Little Red Riding Hood. And suddenly, oops, does that work? Okay, I think it's my initializer for the document that doesn't take any parameter. No, it does. Okay. Yes. I'm gonna have to debug my code, but anyway, you get the picture.
Yes, about how to using custom.
Oh, it's because my document title is already predefined. Duh.
Okay. Okay.
So anyway, here I can even say document title. So here we go. So now we have a document type. We have an attribute title, Little Red Riding Hood. So even though it's a secret, and we can still authenticate because we can see can authenticate to true here. So we do have a secret that we passed on that when they try to observe the object, they think they just got a document object. Completely useless for them. They then gonna try to look at a different object, try to figure out what's going on. And the attacker may spend 3, 4, 5, 6, 12, 16 hours before they figure out, oh, damn, this guy, they have a custom reflectable, probably this. And so you may discourage the attacker. So even though they got access to your system, they may be completely lost, discouraged, or even go back to their boss, say, I was not able to do it. It all depends on the skill level of the attacker, how much time they have, how dedicated they are, or they may just sometimes try to look at 16 or 18 different apps that are on your phone, and they just try to see what kind of information they can easily have access to, and they'll just go over your app. They won't be able to get anything meaningful. They'll just skip over it and move on. So reflection can be really helpful to completely get the attacker off your back or misdirect them, or at least increase the amount of effort that is required for them to extract the information that they want out of your app. Does that make any sense?
Yes, great. I think that we learn a lot of things about how to secure our reflections using this kind of custom what we call custom mirroring, if you can say, or custom reflections. And we keep using reflection, but in our manner, if we can say.
Correct.
and we try to try to make some faked information to the hackers or to the attackers that think about, okay, no problem, this is not a token, this is a recipe cooking attribute type. We try to make some kind of faking the information. We keep using our mirroring, but in our like I said, in our more secure manner, if we can say.
Exactly. So this is really useful for a variety of reasons. And one of the things that we can do as well, alternatively, is to create like a static library for our target. Then
Okay.
we move all of the code that we want to have like secure, custom information or
And
no information at all. You move it into the static library. And the static library is compiled with Swift Reflection none, but your normal code is compiled with Swift Reflection all, which means that any information that comes from the static library will have absolutely no Swift reflection at all. The issue of doing that is sometimes it gives a pointer to the attacker that they at least have the right type of object.
okay.
Because they don't see any Swift reflection for this class, but they see a lot of Swift reflection for other classes, and they're like, well, damn. This object I don't get any reflection of, it must be important. So they already, just by that hint, they can already tell that it's the right stuff. They're in the right direction. So at least by providing a different class name, different attributes and whatnot that are completely not important, it's easier to confuse them.
Yes, great. I think that reflection is great, and something like Swizzling. When you come to Swizzling, also it's good to make some custom call for specific classes or struct at runtime. It's great, but it's usually there is some security issue with this kind of API like reflection, like the techniques of Swizzling. From your point of view, what's the reason why we in Apple we don't think about the security impact of our API in the language like Swift, etc. There is or Objective C. Swizzling come from Objective C. It's not new to Swift, and a lot of developers use Swizzling, etc. in their code, especially in some frameworks. We know a lot of frameworks that use Swizzling. The kind of Firebase Firebase
Well,
example.
exactly. I think you nailed it right there. This is why we're doing it. This is why we build Swizzling and whatnot, is to be able to have those big like analytics library, be able to easily add them to our class to our project, and we just say enable Firebase, and then some kind of magic happens, and then suddenly Firebase is able to know when the view controller becomes visible on the screen. They're able to see the titles. They're able to see which button you press. They're able to capture a lot of information. And this is mostly done because of Swizzling. It's possible because of Swizzling. They are able to swizzle your app delegate, for example. And so
Mm,
when app delegate gets called, they are able to know exactly, okay, the app went to foreground, background, it received a notification. They're able to observe everything that your app is doing. So it's super helpful for third-party libraries that want to do analytics and this kind of stuff. So this is
mm.
why they do it. Um, I wish they didn't, and they forced us to have a bit more custom tracking in our code. I want this view controller to be tracked by this library, and like, oh, I want my app delegate to inform the analytic library that I'm pushed to background, so it gives you some more control over what gets logged in the analytics. But I mean, I do see the value of just being able to have one line in the Firebase enable, and boom, done.
Yes.
So there is value in the simplicity, and I totally understand that. At the same time, from a security standpoint, Swizzling is a big risk, and I think it should just be abolished.
Yes, I think you are right. Your point of view, from the point of view of secure specialists, it's important to. But I know also that's very difficult for people to develop frameworks, etc., like Firebase, like other data analytic framework, to have some alternative for that. Mm, Not easy from my point of view. That's why.
Just Swift UI is already making the life of analytics frameworks super complex because you no longer have the classes that you can observe, and Swift UI
Ah,
is just data. So all they are able to see is that there's some kind of Swift UI view presented on the screen, and that's it. They
mm,
have no idea which view which button gets pressed, anything, because it's all just data manipulation. We are manipulating a data representation of what's going to be displayed on the screen. We're no longer showing a view controller. We just say Swift UI view with this title, or Swift with this button, and then the Swift UI engine, rendering engine, prepares the view and the classes and the controllers and everything that is needed, and everything is kind of like handled for us. So from the point of view of analytics library, Swift UI is a big nightmare, because they can't really. It's much harder for them to extract the information out of Swift UI.
Okay, I'm convinced because I have some discussion with Google Developer Firebase about from some API related to Swift UI, and they make a lot of work to to resolve this issue with Swift UI screens, and I understand now.
Yeah, for sure.
Okay, it's great. Yes.
You also had a question, I believe, that you wanted us to cover today. It was for API keys?
Yes, we would go to the API keys, and before that, we have some discussion about API keys.
Sure.
Yes, and I think that a lot of developers, not also iOS developer, but Android web developers, etc., they try to preserve their API keys in solution like in the application or in solution like remote config, etc. And they think that their API keys are secure. And when I discussed it with you for many times, there is a lot of problem when you have your API keys exist in a server like in Firebase remote config or in your application. That's why my first question: what's kind of API keys vulnerability, if we can say it, in mobile application and also in desktop application, web application, and what most common ways that hackers might attempt to retrieve them?
Well, there's really two types of API keys that we have to think about.
Yes.
There's the API keys that will allow us to reach to a service provider over the internet. So let's say if Google Maps or another service like that is online, and you need to provide some kind of authentication key for the service to provide you with value. So let's say you want to be able to query Google Places. Well, you need a Google Places API key, and then you will be charged by the amount of queries that you do per month. And so this is the first type of API keys, is just network queries. The easiest for an attacker is just to set up a proxy server between your app and the internet. So they just install your app or whatever, and they use your app to do queries, and then they just have a proxy server set up in between. They grab the keys, and that's it, because most likely Google Places and a lot of third-party services, they don't actually do TLS spinning inside of their libraries. So observe you can put a man in the middle with a proxy server, and you can just observe the queries going in and out, and you can see everything that is there. So they will be able to grab the API keys. Surprisingly, service providers like Google, they are not interested in building an actually secure API. They don't give a crap if you have to send your API keys in clear text. And if your API key is stolen, it's actually better for them, because if your API key is stolen and it's used by a hacker to make millions of Google Places API queries on your behalf, well, that's a million queries that you, as a client, will then have to pay. I went through that as a personal story before. My Google Places API key got stolen, and I ended up with my normal bill account, Google Places bill account of like $3, $4, $5 a month. Suddenly, in 1 month, it was $12,000. To Google Places, to Google for like accounting, I'm like, dude, there's no way my app had that amount of queries. They're like, we can confirm that our API has received this many requests with that API key, so you have to pay for it. I'm like, can you please open an investigation? And they did an investigation. They came back with the exact same response. We can confirm that every one of those API calls happened with your API key. Now you have to pay. I was like, what the hell? Like, I don't have $12,000 for paying for my Google Places this month. Like, that doesn't fit in my budget. And they're like, sorry, you have to pay. So if you then, so companies have to either foot the bill and close in some instances, because if I had to receive, like, I don't know, a $600,000 invoice, I would not have been able to pay it. I would have to declare bankruptcy or something. So where you need insurance, like $1 million insurance or something like that, just to be able to pay your Google Places API key that got stolen. And for Google, well, they're laughing because they now are able to charge an extra $12,000 just because your key got stolen. So for them, they have no incentive whatsoever to protect your API keys or to make it more secure or to obfuscate the API key that you're using. They may be doing it for a large contract. Let's say they have a contract with Apple. They may provide Apple with a way of obfuscating their keys or something like that. But for mom and pop shops, they have no incentive whatsoever to do it, just because the more their key gets stolen, the more money they make. They will either make money directly from you, or they'll make the money from the insurance company, but they'll make money. So for them, they have no incentive. So when you're dealing with this, you either have to find a different service provider that will do proper API protection, implement proper API security. There are ways of authenticating yourself. We saw that in the previous session that we did together. There are ways for us to authenticate securely to a server. Similarly, there are ways for us to provide an API key to a server via hashing or P56 signing. So we could sign the request with the private key and without ever sending the private key to the server, and the server would be able to confirm, yeah, it's our API key that is being used for those requests. So there are ways for them to build secure APIs that don't allow the API key licenses to be stolen, but they don't. So it's for you as a developer to either find an alternative provider that takes security seriously, or try to implement your own TLS pinning on top of the APIs. So instead of just using the framework, you figure out what the framework is calling behind the scene, and then you do your own TLS pinning with that same endpoint, and at least you're able to prevent man-in-the-middle attacks.
I understand. And for I know that a lot of developers try to preserve in the info list. A lot of developers in the info list, and also in the application, in the code.
That's right. That's mostly for that goes into the other type of API keys, because the first type of API key is the one that goes over the network. The second type is when you have to include, let's say, a library like PDFtron to be able to do PDF inside your app. That library needs an API key in order to prove its use. So you need to have the API key locally in your app. There's no choice around that. You need to have it built in because you want to be able to use that API, that library offline, or there may be not even any networking code in your app, maybe none at all. So for those apps, the key need to be included. And this is where a lot of developers do the first mistake that you mentioned, putting their license keys inside of the info P list. So level 0, you have your string as an info P list key. Your license key straight into info P list. Why it's not secure is because anybody downloading your app, when they download the app, it's in a format called IPA. So the IP is just a zip file. If you rename IPA to .zip, you can unzip it. And then inside of that zip, then you have the info.plist, that is the file called info.plist, and that is inside of the content of your app. And you're able to view that with any plist editor. Like you double click that with Xcode, for example, or you print the bplist on the command line, and suddenly, boom, you got all the values that are right there. So from any app downloaded on the App Store. So if you store your API keys or your license keys inside of info plist, easily accessible by any hacker just looking at unzipping your IPA that they download from the App Store. There's a command line tool called IPA tool that allows you to just specify the bundle ID that you want. And after you authorize the purchase on your own App Store account, you use IPA tool, you sign into your Apple account with IPA tool, and then you can say download IPA for this app that I have on my account. And boom, you got the IPA bundle straight there, and you're able to have access to all of the files that are in that bundle. So it's easily accessible to any hacker with the minimum of training. They'll be able to access it. So obviously you don't want that in your info P list. So the next level after that, what I see people is, well, I'm not going to put my key inside of the info.p list directly. I'm going to create an environment variable that populate my info.p list from the CI/CD pipeline. That's going to be much safer. And
Yes.
without realizing that because the environment variable gets replaced with the actual value at compile time, instead of the info.plist list, your API key is still there, and you still have the same problem. So great, you store the license key inside of your source code, inside of the info.plist list, but it's distributed on the App Store instead of the
Yes.
info.plist list. So it's no longer, you haven't done
It's not
anything to
secure.
protect it.
Yes, it's not secure, but there is a
The
lot of
next step
tutorials
you
about it.
mentioned as well is putting it straight into the source code. So then people
Yes.
are like, okay, I'm not going to put it inside of the info.plist list. I'm going to put it as a string inside of my sources. So
Yes.
at least it's compiled right along with everything else. It's not inside of my strings array. It's not inside of the info.plist list. So it's much harder. But again, the same way that the hacker got with the IPA tool access to your IPA file and were able to access your info.plist list, the binary that is read by the iPhone or the Mac have an internal file format, like ELF, for example. And
Yes.
inside of these file formats, they have different sections of data. One can be a code section, another one can be a data section, and there's a special section called a string section.
Okay.
So using OBGC dump, the command line tool, they can dump all of the strings that are inside of the app. So they use OBGC dump, the name of your executable, and then all of the strings that are built inside of your app are dumped on the screen right there in one shot. And what is this? And so if you had an API key that is inside of a string, they're gonna see that string fly by. Maybe they will not notice that it's a license key, but if you're dumb like Apple, like Google, all of your Firebase API keys are all gonna start with the same 3 or 4 letters, like FB underscore blah. So
They
then
can
any
they can
string that
pretend.
starts with that prefix, and you're like, these two are API keys, done, super easy to do.
Yes.
So again, Google, fantastic job, guys. Well done. So just dumping the strings of your object dumps all of the license keys along with all the other strings. It may be confusing if you have a lot of strings that are in your source code, but if you have a very simple app, dumping the strings of your very simple app will make it super easy for us to get any of your API keys outside. So the next step after that is to store the API keys as array of uint8 inside of your source code. So
Okay.
essentially, you take your string and you dump it as UTF-8 data object, and then you figure out what the byte values of each of those UTF codes are, and then you create an array of UTF-8 string. And so in your source code, it's like static let my
Yes.
key equal array of uint8 close bracket equal, and then open bracket, and then just a bunch of numerical values that represent your characters. And
Yes.
then at runtime, you just take this value, you reconstruct a string with that data object,
Of
and
the
you're
array.
able to use it. It is indeed much better because string dump will no longer at least show your strings.
Yes.
But then they are kind of able to, if again, they know that you're using Firebase and they want to get access to your Firebase key, they can look at all of your binary object itself still in binary form, and they can look for FB underscore. Now, if you use an array of uint8 object or an array of uint8 value, is the exact same thing within the binary object itself. It will still look as your actual
Yes.
string, because those bytes that you just created, those uint8 bytes, are actual characters, ASCII characters. So now, if they go and search your binary object for FB underscore, they're going to find where that key is defined inside of your uint8 array. They're going to be able to find the match one-to-one. It's no longer going to be in your info plist. It's no longer going to be in your string dump, but they can still look for a pattern. If they know which provider they have, they can look for that pattern instead of the binary itself, and they might be able to find it. Now, obviously, if the key doesn't start with a very obvious pattern like FB underscore, is just a numerical key of some kind, it's going to be completely hidden. It's going to be very hard for them to know where or what it is, but it's still there for some keys that have patterns. So next step after that is to use some kind of encryption, obfuscation of your keys. And this is the example that I prepared for you.
Yes. Yes, the practical part, and I think that this is the strategy that you recommend to protect API key, especially in production environment. And we can go maybe with the practical part. Yes.
Absolutely. So first, if you don't know what you're doing, find a library, a third-party library that does it for you. Something like Swift Secret is a good for that. We're going to provide the link in the YouTube video, the documentation
Description, yes. Yes.
description. But let's go ahead with our description today. So there's two types of protection that we want to do. The first one is when we want to provide a library. So we are creating a library that detects CDF on the hard drive, on the phone. So if we want to verify if the phone is jailbroken, we're going to have a library. We're going to create a library that is going to detect CDF. So we're going to look at various paths on the file system like /bin/cdia or /etc apt/cdi config. So we're going to look through the file system to find any traces of the CDI. So this is our library. But when I'm giving you that library, and you're paying me for detecting the CDFs or you're licensing my library, I don't want to give you how I'm detecting that, right? I want to hide my secrets. I want to hide my secret sauce, my recipe for detecting CDF. But if I just give you the list of all the paths as a string, it won't be very helpful for me because you're going to license the library once, maybe 1 month, cancel your membership, and then you're just going to re-implement yours with the list of paths that I'm looking, because this is all I'm doing. I'm just looking for a list of paths.
Yes.
So in that case, what I want to do is hide those strings. So the one good way of hiding those strings is a script called generate protected string that I created here.
Okay.
So what it does is that I can create an array of all my strings at the top of my file.
Okay.
I can define the keys that I want and then the actual value of the strings. Like that could be any string that you want, right? It doesn't matter. And then when I'm gonna build the project, so if I go in my build phase of the project, I have a phase here that's gonna run my generate protected strings script, and it's gonna create this protected string generated Swift file. So directly, every time I build my project, I can go and edit my strings at any point in time. And when my project will be built, my internal protected string generated file here will be updated. So if I go here and I select my right target and I say build, you're going to see those values here are going to change with the new value that I modify. So I can go here, I can modify my strings, and I can rebuild the generated the strings here. And every single time that I modify it, the file is going to be updated with the very latest version. Super convenient because there's no manual command line to run. Once your script is in place, you can maintain your array, you can develop it. And inside of the source, the binary file that we're distributing, all they see is a bunch of uint8 arrays. Your string is not showing up anywhere in there because B5 is not an ASCII code. It's not within the first 128 characters, and yet my strings don't have anything that are not ASCII code. So we know that our strings, I will not tell you what I know, are not ending up in the protected strings file as is. It's encrypted. And in our case, we're actually using AES-256 to encrypt our strings files. And we are also using some clever scripting to dynamically create the list of values for each of the strings. So if I add a new key in here, so let's call it Facebook API, and let's say the value for that is FB underscore and a bunch of values. Right now in our struct, we don't have any key for FB, but as soon as I build, it's going to add my Facebook API key. So it's super convenient to do. So this script is just a command line script. So essentially I just create a command line script that's gonna look at the command line parameters, and it's just Swift code. Reads the file, the file path that I want to use for the output. It grabs the list of protected strings that is here, encrypts the protected strings encodes as a JSON encoder, then encrypts it with my symmetric key that I just randomly generated, and then formats an output. Like this is the output of this is the exact output of the protected string file. You can see at the top here. So it starts with script, import foundation, import blah blah, and then we have the exact stuff here. And if we did, for example, import, I don't know, AppKit, and we regenerated, we can find that AppKit has now been added. So this is literally just the file as is, right? So we're just deciding how we're going to create that Swift file that we're going to be generating. We can input whatever we want in here, and it just has some template code to be able to decrypt and open the file that we just encrypted, which is just essentially this code here. So feel free, guys, to use that example in your own project. I'm okay with that. No copyright involved. You can just grab that generated protected string. You go and add it as a build phase for your project, and that's going to create that protected string. And the way to use it is very, very simple. You just say protected strings, and then you say Facebook API, and that's it. And then when you're gonna run your project, your secret is going to be accessible to you. Simple like that.
Yes.
So that's super easy for us to use, and it's convenient. The problem is a type of attack that we call memory dump. So we talked about runtime application security in the first part of this video today. And when they do a runtime, one of the type of runtime attack that they do is that once the application is running, they do a memory dump. And in the memory dump, everything that is in memory is directly accessible. You're able to see everything. So see if you had a bunch of strings, like the protected strings, that were decrypted once at runtime. So because it's a static let, it gets created only once, and then what the protected strings is a simple array of strings, right? So we have a struct that has a bunch of strings in them. It's decoded once at runtime, and then once it's decoded, it's available in the runtime memory. So when they do a memory dump of the process, they will see all of our strings, all of our protected strings are accessible right there. So from the point of view of distributing your API keys, it's great. But from the point of view of defending yourself against a runtime attacker, like a Pegasus spyware or a malware, it's completely useless. So they'll be able to get all of your secrets. So the next step after that is to actually protect your string even at runtime. Essentially, you want to keep them encrypted until needed. So every time you need your Facebook key, you can decrypt it, use your Facebook key, and then destroy it. So the way to do that is to create a class like this, where essentially you still have your magic. It's fine. You still have your symmetric key, but your runtimes, instead of having static string for each of your value, you have a variable that will be decoded at runtime. Okay. So this because it's I created this dynamic accessor here. The string will be decoded every single time I access the secret Firebase API key. Every single time I want that secret Firebase API key, I'm going to have to open Sesame that uint8 array. So this is going to be every single time. We can put a breakpoint in here if we want to. And what we will see, so let's go with our secret, runtime secret. And we want the Firebase API key. And we're going to even do something better. We're going to say button, show my key. And we're going to re-access the same key here. So we're going to do a print runtime secrets, the secrets Firebase API key. So every time we press the button, we should see a log entry now that will show the API key.
Okay, great.
First let's remove the breakpoint just to be able to prove what we're doing. So every time I'm going to press that button, I have the value hello from JSON that prints out, because that happens to be my secret. And I see the same secret is here, hello from JSON. So every single time I do that, it prints. But to prove that it's doing it at runtime, we need to put a breakpoint. So now if I go back to here, we can see that it has to open Sesame for having access. And if I do it a second time, breakpoint is hit again. So every single time it needs to have access to the value, it will at runtime decode this array, give me the value, and then if I destroy the value right away because I just use the value for an API call, or I use the value for the licensing the library, and then after that they do a memory dump, they no longer have access unless they do the memory dump at exactly the time where the value was decoded but not yet sent to the library, but it has to be like right there. But if they do it after the app is launched and all your libraries are already initialized, They won't have access to any of your API keys. They're already been validated. Everything is used. So, and then you can, using custom reflector and custom convertible, the same thing that we saw in the first phase of the video, they don't even know that those attributes and those values exist. They don't even know that those attributes are accessible for them. So you can redirect them to somewhere else in your app, and then they don't even know that these attributes are getting called.
That's great. Great.
So this really, really protects your keys. Now, the problem that you probably are started to think about is, well, Dave, if I just have an array of strings like that, won't that script get added to my GitHub repository? So if my source code gets leaked, they have access to all of my keys, and you'd be completely correct. And so this is the downside of using something like protected strings with the keys built inside of your scripts, is because that script is fairly complex. Like, you don't want all your development team to have to manually create that script on their side in order to be able to do that. So you will want to commit that script to your CI, to your GitHub repository, or to get to avoid this. But at the same time, you don't want necessarily your secret. Now, in the case of like a CDL library that I mentioned before, where it's just your secret files that you don't want to leak, and these would just be like file path, I don't know, like /bin/cdia, you don't really care if that gets into your repo, because that's fine. But if it's a Facebook API key, then you are worried about that. You don't necessarily want that in your Git repo. So this is where, in my runtime secret here, what I've done is I built, I used the CI/CD pipeline to create an environment variable that will have my secret, and my script itself doesn't. So I can commit that script to my repo, because it doesn't have any secrets in it. It has a template to be able to generate my secrets, but it doesn't have my secret. The way it does is that it looks at the environment variable to be able to build it. So when we go into the build phase of the app, I don't even have it here. Actually, my CI/CD pipeline should have a script to do that. So I'm going to open a terminal window, and we're going to go into our project. So cd dev security with valid, and this is security 202. When you go into the script folder, you can see that I have my generate runtime secret. And if you just do this, it will tell you that you need to provide a path to where you want the file to be generated. So security 202, and the file is runtime secrets generated.swift. And it tells you we need that environment variable to be defined, so we can define it. So this would be, the export statements would normally be part of your CI/CD pipeline integration. So if you go in GitHub, you can say, when I build this repository, I want this environment variable to be defined, and this will be the value of my environment variable. So we're just manually defining it here. So secret Firebase API key, and the value for this will be Facebook. And then we can say the same for the other variable key. I think the other variable was named secret other key. So we're going to do the same thing, called secret other key. And that value for this will be hello from env. So now we have those two environment variable, and if we rerun our script, everything works. Oops, I have a typo. Yeah, my Firebase API key had an extra underscore.
Yes.
And failed to write template. Great, it doesn't exist. What did I screw up? Oh, I'm in the right. I should not be doing this from the script folder. I should be doing this from here. Generated runtime. We want security 202 runtime secret. There we go. So now when I go in here, I have my two keys. My stuff here has been updated. Great. And let's just verify that this works. So if I update my secret, and let's say I say
another secret, yes,
hello Walid, and then we regenerate this, the generated runtime here will be different. And then if we run this, it says hello Walid. So whatever we use as environment variable, when we rerun our script, it updated this file here, and then at runtime, we're still able to get access to our values. At runtime, decoded, everything is safe, is secure, and then it's managed by the CI/CD pipeline. The problem now is that our developers,
Yes,
they need to be able to generate that file on their side, because that you will want to have that file, and these two generated files you want excluded from your GitHub repository.
Yes.
Because they contain the secrets. So how can I have my developers work? Well, what you can do is you can create a file that you call dev secrets, and that's your JSON, and it contains all of your secret that you want your developers to know. So you can even have different secrets for your developers than your runtime environment. So you can tell your developers, you have a developer environment and you have a runtime environment. These are your secrets for you to be able to access your developer environment. And the CI/CD pipeline is the only one that has access to the production secrets and the production API keys, and they run a completely different environment. So you can have different set of secrets for production and development, and this is how it's done. You can do it there, and then your developers, what they will do is they'll just add the file path here, and then as they rerun the target, they'll grab the secrets from the JSON file.
Great.
So you can have just again using that script, it either works with 2 or 3 command line parameters. So at runtime, it just verifies how many command line parameters were provided. If there were only 2 command line parameters, then it grabs the keys from the environment. If there was a third command line parameters provided, it grabs the file from the JSON file that is specified on the path. So this provides the solutions for not having your secrets in your Git repo, having it injected in the CI/CD pipeline for the production environment, yet still having the convenience of having a small file given to your developer. So when your developer onboards on the project, you just give them that small file. You say, make sure that you have a small file inside of your local repository and run this command line once, or every time that you need to update or add a new secret, you can just rerun that command line, and it's going to re-update produce the runtime secret generated file for you on your side.
Yes, great. I think it's but maybe some developers will think, okay, but every time that I need to learn the application using the Firebase, I need to regenerate this. But you can make some scripting to do that in the pipeline, and it will be
yeah, absolutely. You can make some script to do that, or you can do like I've done here, and you just update your git ignore file.
Yes.
So that it will ignore your dev secrets file. So you can change branch, you can create another branch, you can do all your development, and unless you create a brand new copy of your GitHub repo, that file will always stay there, and that's fine. And then when you open your Git management tool, it will simply be ignored if it's being modified. So your developer can create create that file once, and then unless they modify it themselves, they don't even have to rerun the generated file. Yes. Or like you said, we can also go in here, create another build phase.
Yes, in
so we say new run script phase.
In the pre-compilation, I think it's before the compilation, because maybe they need to
exactly. So create
sometimes
runtime secrets generated Swift, and then just move that all the way to the top, and then this is where you say, oops, unset SDK root, and then you give your src root scripts generate runtime secrets .swift, and then you need to provide the path to where the file will be generated. So that is security 202 runtime secrets generated .swift. And in our case, it will be using dev secrets.json.
Yes.
That is in src root as well. And then if we run this,
maybe
not. Maybe I screwed up something. Let's see. No such file or directory script. Anyway, you get the picture.
Yes.
We can troubleshoot this after the call, but the point is you just create script like this that if the dev.json file is present, it uses dev.json. Otherwise, it calls the same function, the same script without the extra command line parameter for the CI/CD pipeline. So either way, it will work. But yeah, you can absolutely do the integration directly in your build phase, like you mentioned.
Yes, great. I think it's a great example to play with the API keys and to have much secure using of our API keys, not passing by remote config Firebase
Well,
to retrieve this API keys yes.
Firebase remote config is useful for a bunch of stuff, especially when you want to do something like A/B testing. You want to have
Yes.
multiple bases, and then you want to do an A/B test, and then after a while you realize that the B variation of your view is more useful than the A. You want to disable it. So via Firebase remote config, you can disable variation A, and then everything runs on variation B. So that kind of stuff is really useful for being able to dynamically modify your app after it's been published. But deploying API keys via Firebase remote config, that's not what it's supposed to be used for. Same thing with maybe it would be useful, for example, for TLS pinning. So where you are providing a public certificate of your API, and this is what you're going to be doing the pinning against. Anything that it really doesn't mind if it's observed or if it's captured by man-in-the-middle is okay to distribute via Firebase remote config. If you are publishing API keys via Firebase remote config, I would at the very least say please encrypt your data before putting it into Firebase remote config, and then decrypt it after you receive the value on your side inside of the app. Just make sure that anything that you put in Firebase remote config is okay for you to be publicly observed by a hacker.
Okay, great. Thank you. It was a very special episode, very practical episode with two great topics such as runtime attacks using reflection. How we can secure our with custom reflection. We discover a lot of level of reflection attacks. How we can secure with what we call the Swift reflection metadata, etc. The anyone with and after that, we discover the API keys, how we can secure API keys, because there is a lot of confusion about secure API keys. And there is a lot of articles that we discovered with you when we preparing to this episode about. There is something sometimes that some people have what we call not the whole pictures. They speak about things that they didn't understand very well. They speak about how we can regenerate files at runtimes, but how we did it with the CI/CD, how we can handle with our developers, because this is the question that we should suppose when we work with API keys, and I think it's great for this episode. I don't maybe
Sorry.
no problem.
So the one thing that people also have to realize is
Yes.
if your developers have access to be able to create builds inside of, like, let's say they're able to push a branch to CI/CD pipeline, and your CI/CD is able to build
Yes.
their target. The build scripts are usually part of the GitHub repository itself. So of your Git repo. So you have a build script that builds your target, and then runs it on the CI/CD pipeline. And if your CI/CD pipeline is injecting the production value for those other branches, what you will end up with is a developer that is clever, that wants to have access to the secret, will be able to, in his own personal branch that is not yet merged into the main line,
Okay.
directly go and modify the build script to be able to echo the value of the secrets. And already I can see people say, Dave, that's not true. GitHub will ultimately filter the output if they see the secret variable inside of the output. Yes, to some degree. If your developer is clever, they'll simply take the value, base64 encode it, and then echo it. So your CI/CD pipeline will run. It will grab the CI/CD secret from the environment, the secret values, and your script for the build script that the developer will have modified will grab that value, base64 encode it, echo it back to the output logs of your build, and then your developer will just grab that base64, grab it back on their side, decode it, and they have access to your runtime secret. So
Yes.
if you are really worried about your developers gaining access to runtime values of production code, you will want to also make sure that those secrets are only accessible from a branch that has been peer reviewed. So at the very least, if a developer wants to have access to the runtime secrets, they need another friend working with them to go through a PR review, accept and merge to mainline. But then there are traces. You can tell who the guys are. You can tell this is this developer and that other developer that work together to get access to the secret when they shouldn't. And then you can fire him.
Yes.
But if you don't do that, then all the developers, all they have to do is modify a few of the command line, a few of the build scripts to grab that environment, base64 encode it, print it back to the logs, and then they can just delete the branch and you have no idea what happened. Even worse, if depending on how your CI/CD pipeline is built, maybe they can even go and delete runtime logs of previous builds, because sometimes your GitHub action will run, it will generate an artifact that this action has run at this time, and then you can go in GitHub as a developer and you can just say delete this action log. So you have no traces that this happened because your logs are gone. Your CI/CD script may have been modified by the developer to make sure they don't generate any undue artifacts to a logging server of some kind.
Yes.
So you really have, when you talk about API security, you really have to take a holistic view of everything that is involved. Like, can the developer generate a production build? Can the developer modify or run a production build or get access to production environment variable from the CI/CD pipeline if they modify it? Do they have access? And you also have to consider, do I trust enough my developers to, in some companies, like a 2 or 3 guy company, the one developer is most likely the one that set up the CI/CD pipeline, and he has access to those keys. He probably even have them. He has a local copy of those values inside of his 1Password on his machine. So, do you really care if he has access or can modify the CI/CD pipeline? Probably not. But then you have a new onboardee that you just hired, a new hire that comes into your company. He passed the security review, but at the same time, do you really trust him with the keys of the kingdom? Probably not. So this is where at some point you have to evaluate, like, how much of the am I ready to give to that new employee that's just joined?
Yes.
Ready to give him the keys of the kingdom? Am I able to give him to the secret? And if you have your CI/CD keys or a secret inside of your pipeline, you probably don't trust them enough with those secrets. That's probably the end. You probably want to keep those secrets, even to some of your development team. So make sure that you also review your CI/CD pipeline permissions so that only master branch that has been peer reviewed has access to those secrets, not all branches. So you need to really take, like you said, a holistic view of everything, your entire environment, and everything that is involved.
Okay. Thank you, Dave. It was a great episode. Thank you very much. And we have other topics that we discover in the next episode, speaking about what we call secure enclave, and also maybe we speak about Touch ID, Face ID, something like that, and how it. And
Yeah, I'd
that's
very much like to give a demonstration of how to do actual encryption. Like, because right now, in those, like, if you grab the sample project, you can see how I've done the AES encryption, but it's a little bit confusing about how it actually works under the hood, maybe. So
okay.
I really want to go more in depth about how to do symmetric encryption, asymmetric encryption with public-private keys, because we touched a little bit of that in the first episode that we worked together.
Yes.
And I also want to provide an example of data authentication. Can
Yes.
you prove that a piece of data comes from Walid
Yes.
without having access to Walid at the moment where I'm having access to data? Can I validate that? So it's called data authentication or cryptographic signing. So
Yes.
I really give an example of that as well.
Okay. Okay. Great. And thank you, Dave. See you soon. Thank you.
See you
Bye.
soon. Cheers.